Derivatives are so important. We need to be able to evaluate them quickly. So there are many, many rules for derivatives. First one we're going to look at is the power rule. This is one of the most important. So what I've done is taken a collection of derivatives that you've calculated and all their answers. And we're looking for a pattern. The derivative of x squared is 2x. Derivative of x cubed is 3x squared. What's happening with the exponent? Used to be 2, now it's 1. Used to be 3, now it's 2. Well, that's interesting. Used to be 1, now it's 0. Because there was no x there, so that's x to the 0. So is it true that the exponent is simply getting lowered by 1 every time? Does that work? X squared, x to the 1. 2x to the 1, 2x to the 0. Goodness. 7x cubed, x squared. It looks like the exponent's going down by 1. So when you have a function, y equals ax to the n, the new one has an x to the n minus 1. And what happens to that exponent? Because we're changing the number out front. Is it simply that that number gets moved out front? Is that where the 2 came from? Is that where the 3 came from? Goodness, let's check that. Let's try this one. If we use that rule, multiply by the exponent, there's our 21. Lower the exponent by 1, there's our x squared. Oh my gosh. 8x to the power 1, 6x to the power 1, 2x. What's going on with the 4? Do you see any x's over here? No. So when we multiply by the 0, it just gets rid of it. So look at this. This is amazing. We have a beautiful derivative rule. When you have something in the form number x exponent, you multiply by the exponent. That's where the NA comes from, and then lower the power by 1. For those who want to know why, watch this slide. If you don't care, go on to the next one so you understand how. Okay, let's go to our definition. F of x plus h minus f of x all over h. Our function is x to the n. The derivative, f of x plus h is x plus h to the n. X plus h to the n, we could use Pascal's triangle to expand that. Am I serious? Well, we'll get a pattern anyway. How far should we go? We'll go dot, 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 and say somewhere down here is x plus h to the n. What's the next number going to be? This is x plus h squared, x plus h cubed, x plus h to the n. Okay, so we would end up with x to the n, then n, x to the n minus 1, and there'd be an h involved. Then we'd have some number. Turns out it doesn't really matter. X would go n minus 2, h would get higher. We'd keep going until we got all the way to h to the n. So this is what x plus h to the n looks like when it's expanded. A little bit messy because we don't know what the numbers are, but it really doesn't matter. X to the n over here, all divided by h. Now watch this bit of magic. The x to the n gets eliminated. Then, can you see that absolutely every term has an h in it? So we can divide by h, lower all those exponents by 1, and here is the marvelous part. H goes to 0. H goes to 0. H goes to 0. So all these terms that will have an h in them get wiped out. The only term that didn't have an h was this one because in the beginning it only had one h, and that h got eliminated with the h in the bottom, which means all those go to 0, and the only thing you're left with is n, x to the n minus 1. Magnificent. How do we use it? So our rule, if you have a function in the form number x exponent, the derivative, multiply by the exponent, nax, lower the exponent by 1. Multiply by exponent, so 120, lower exponent by 1. What happened to the 7? The 7 had no x's, so that's x to the 0. And when you multiply by 0, what do you end up with? 0. And we just don't bother writing it. Okay, Here's where you've got to be careful. This is in the form number x exponent. This is not, nor is that one. So you have to make sure the only time you can use this rule is when things are in the right form. So we're going to have to change them. 2 over x cubed, 2x to the minus 3, 3 root x, x to the 1/2. Now apply the rule. 5x to the 4 minus 6x to the minus 4. How did that happen, my good Canadians? If you are thinking about a thermometer and the temperature was at -3 and you go down by 1, where are you? That's where the -4 comes from. All right, this one. 1/2 times 3 is 3 over 2, and then 1/2 minus 1. 1/2 minus 1. We need a common denominator, wouldn't we? Multiply top and bottom by 2. 1 over 2 minus 2 over 2. That's where the -1 over 2 comes from. Now, we're not real big fans of negative exponents. If I asked you to evaluate this when x was equal to 2, you'd find it quite difficult. So please make sure that you rewrite it, put your negative exponents in the denominator. So what am I asking you to do here? If you have a negative exponent in your answer, I would like you to change it. So those negative exponents just came down here instead. So we're saying instead of multiplying by x to the -4, we're dividing by x to the 4. It's the same thing. There is one last thing I'd like you to do. If I'd asked you to evaluate this when x was 4, 4 to the 1/2, we have to think about. X to the 1/2 is the same as root x, much easier if we read it that way. So make sure everything is written in the right form, number x exponent. So fractions, you have negative exponents. Roots, exponent 1/2. Take the derivative and then clean it up. We don't really like to work with negative exponents, so we write them as fractions instead. And we don't really like to work with x to the 1/2, we'll write it as root x. Let's do one more. X plus 1 cubed, is that in the right form? Oh, no, 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 you don't see a bracket over here. So Pascal's triangle. Coefficients would be 1, 3, 3, 1. Exponents on x, 3, 2, 1, 0. Okay, and please be careful. We haven't taken a derivative yet. This is still y, we're just simplifying. Now, each one of these is in the correct form. Take the derivative. Multiply by your exponent, lower the power by 1. Multiply by exponent, lower the power by 1. Multiply by exponent, lower the power by 1. Multiply by exponent, lower the power by 1. All right, so today, many more questions because you are much quicker. So use the power rule. No more using the definition of the derivative. If you try that on today's work, you'll be at it forever. So use this power rule to find derivatives. Should be a good day for you.